Gravity. No one knows why it exists. It is responsible for just about everything that happens in this universe, yet we truly have no clue why. We just aren't that smart yet. However, we do know that it exists, and we know that any two masses are attracted to each other by a gravitational force. This was first published by Sir Isaac Newton, who went even further to find that these forces of attraction were directly proportional to the masses of the objects and inversely proportional to the distance between the two objects. That is, the larger the masses, the larger the gravitational force, and the larger the radius, the smaller the gravitational force. He developed the universal gravitation equation F equals g m1 m2 divided by r squared in 1687. No one knew yet what the constant g was, it was just thought of as a constant. I wanted to know what it is, so I turned to our AP system. All I got was a number, 6.674 times 10 to the negative 11th Newton times meter squared divided by kilogram squared. That literally tells me nothing. I want to know why is this number that number, so I must dig deeper, which means I must go back in time again. After Newton came along Henry Cavendish, a British natural philosopher, chemist, and physicist. This guy was super smart. In 1798, he wanted to calculate the density of the Earth, so he set up the famous Cavendish experiment. He made use of a balance developed by the geologist John Mitchell to measure the force of attraction between two sets of balls. Here is how it worked. Cavendish had two 1.6-pound lead balls attached to either end of a wooden rod suspended from a wire. He also had two 348-pound balls fixed equal distances from the wire. He even covered his experiment in a thick wooden box with two holes for observation to prevent interference from air currents. Now let me take a moment to clarify that the force of gravity is very real. I exert a gravitational force on everything else, and everything else exerts a gravitational force on me. But what keeps everything from colliding with me are opposing forces like friction and gravitational pulls from other objects. So, in Cavendish's experiment, friction has been almost entirely removed. Now, the small balls are free to move towards the larger ones, causing the rod to turn and twist the wire. Knowing the torque, or twisting force, of the wire, the distance and time the bar rotated, and the weights of the balls, Cavendish was able to make his calculations. Here are his original measurements. Ironically, he found the density and mass of the Earth, but never recorded g. The value was not actually documented until 1874, when Cavendish's experiment was replicated and g was found to be within 1% of the modern-day value. So though the measurement came from Cavendish's experiment, he did not discover it. Sorry, Henry. To show that both Newton's original concept and that Cavendish's experiment work, I replicated it to the best of my ability. As it turns out, F equals g m1 m2 over r squared can be rewritten as g equals 2 pi squared L theta r squared divided by t squared m. This is accomplished through substituting kappa theta over L for F, where K, or kappa, is the torsion coefficient of the string and theta is the angle the bar turns from the rest position to the equilibrium point, measured in radians. K can then be replaced by 2 pi squared ml squared theta divided by t squared, where L is the total length of the bar in meters. With some rearranging, the equation becomes g equals 2 pi squared L theta r squared divided by t squared m. G is the gravitational constant in Newton meters squared divided by kilogram squared. L is the total length of the rod in meters. Theta is the angle in radians the rod rotates while oscillating, which will be explained in a moment. R is the distance in meters between the equilibrium point and the center of the fixed mass. T is the period of oscillation in seconds, and M is the value of the larger mass in kilograms. If you want to see a more complete explanation of the derivation of this equation, there is a link to an article in the description. So moving on to my extremely simplified version of the Cavendish experiment, I used 2 bowling balls and 2 steel balls. Here are my measured values before the experiment. The main goal is to get the force of torque from my fishing line to match the force of attraction between the masses, so that the rod can oscillate around an equilibrium point. It oscillates because the momentum of the ball moves it past the point where these two forces are equal before it is pulled back by one of the forces, either the force of torque or the force of gravity. When it reaches the equilibrium point again, it still has momentum and so moves past, and this process continues forever and forever. Obtaining this oscillation was much harder than one might think. I had many instances where the torque force was not great enough, so the two just became permanent friends. In other instances, the force of torque was too great, causing it to swing full circle. It was also crucial not to disturb the system with any air currents or vibrations, which meant me leaving my camera on time-lapse mode and coming in and out of my room only to stop the camera or readjust the bowling balls. Finally, I was able to get it to oscillate around the point after many, many tests. Goes up, and it goes back. This continues for hours, but I'm only showing a small portion of the test just to prove that it worked. Eventually, I was able to get this angle of 3 degrees or 0.0523599 radians, a radius of 0.17526 meters, and a period of 31 minutes or 1,860 seconds. When plugged into the equation, I get a value of 9.018 times 10 to the negative 10. Woohoo! Wait, why am I celebrating? Because considering the value of g is so incredibly small and there were large uncontrollable variables in my experiment such as air currents or the frame rate of my time lapse, which would cause error, it is in the very close ballpark of g. Here are the two numbers written out for a more clear comparison of their difference. Science on a budget does not always get you the right decimal. I will wrap this up by explaining the hidden g many people are not aware of. When we want to find the weight of an object on Earth, we are told to multiply the mass in kilograms by 9.8. 9.8 is actually just the mass of the Earth multiplied by g and divided by the radius of the Earth squared. Now Cavendish can actually help us out here as he found the mass of the Earth. Thanks, Henry. This also shows that gm1 divided by r squared is the acceleration of mass 2 as caused by mass 1, or vice versa. Hopefully, even though this video got no one any closer to understanding the source of gravity, it helped you understand that g.